Hey, AP Physics C. This is going to be a quick three-part video. I don't know how quick it's going to be. Part 1 to be a quick summary about work and the calculus. Part 2 to be question 18. Part 3 to be that long one. So here's a quick summary. We know work is a force times some kind of like distance. Normally, nothing's changing. Then we have two kind of breakdowns. If we're given, for example, you want to find the work. So if work is the goal and you're given a function, work is the integral of function times dx. So that's if you want to find work, usually integrate force. If you want to find force though, it's the opposite. It's the derivative of work over the position. Solving for x, you get work over x. Now for us, work for us is usually kind of like potential energy. So to be du dx, I'm going to put a little star here because positive and negatives matter. By that, I mean, if you have, let's say, a positive force, this might mean you have a negative change in potential energy because it's getting faster. So that negative is in there, but it doesn't really matter much when you do the actual calculus. You just add a sign in front of it. So in summary, to find the work from a force and a distance function, you integrate. To find the force and potential energy, you derive. Let's see it in practice. And go. And that's the conf of knowledge happening for number 18. We're given a potential energy function. We see something at 20 meters, it moves 10 meters. We don't know which way. And we're going to try to figure out how much force is there. So the first thing I'm going to do, along with the one from Miss Tarantola there, who's awesome, you're going to find out which way is it going. So it starts at 30 meters. It's either to go 10 left or 10 right. And to do that, I'm going to look, and I'm going to say that I'm going to say that the work is the negative change of potential energy. So we're going to figure out which way it's going. I'm going to put in the x values of 20 meters, which is where if it goes left, it goes 20. If it goes right, it's 40. And when it starts at 30. I'm going to write down what potential energies I get. At 20 meters, I get negative 20 joules, let's say. At 30 meters, it's negative 13.3. And here it's negative 10.
Mm-hmm. And you're just doing that with the equation?
I'm just putting this equation. I'm using negative 400 over x.
Okay.
All right. So my logic here is, again, which way is it going? We're looking at this. This is negative 20 joules of energy. This is negative 10. That's negative 13.3. This is obviously higher than these two. If you were to graph them at 40 meters, it has a potential of negative 10 joules, then negative 13.3 at its normal position, and negative 20 down here. Negative 10 is higher than negative 20. So imagine like I had a ball here. Would it move towards a higher potential energy or lower? And the answer is probably lower, because it's going to gain kinetic energy. So I know it's going to move left. So my summary is it moves left because work is the negative change of potential energy, aka it's going to change by positive, whatever, 7, let's say. So it's going to go to the left, it's going to go to 20 meters. 20 meters is the position. If you were to graph it, you get this kind of function for potential energy is a distance. If it was a ball, you place it right here, it would not move up the ramp and move down the ramp. So that's why I know that secretly the position is 20 meters. Now, I'm actually going to solve. Looking at my first point, I'm trying to find the force. Force is du dx, kind of the negative version of it. So I'm going to take the derivative of that. That's going to equal negative 400 over x, which is going to be x squared. A negative comes in front.
Or is it over n plus 1, so it's over negative 2, so is it 200?
Nope.
No.
It's going to be 400 1 over x.
Yeah.
Same as 400 times x to the minus 1.
Yeah.
That becomes negative, and this is negative 400, so that becomes 400 times -1 to the x to the -2, and that's what I get here.
Okay.
Are you cool with that or uncool?
I mean, isn't it n plus 1, actually n plus 1 over n plus 1, so it's over 2?
No, that's integration, not derivative.
Oh, right, I'm stupid.
That's
Okay.
right. We're going to edit it out. So no,
All right, yes. Okay, yeah, make me look smart.
So now I'm going to put 20 in there because I know there's one left. And I get positive 400 over 20 squared. And that gives me positive 1 Newton. And that's my force, and that's the correct answer. Cool. And now for number 21. This is going to be a unique little situation. Some kids in class were confused about the plus C or the bound, so I'm going to do both. I'm going to have the same answer. So on the left-hand side, I'm going to do what's called, I'm going to integrate with no bounds, but I got to figure out the C term. Here I'm going to integrate with bounds. So the whole point is we're trying to find the expression for the velocity at some time. Not the final velocity, just the velocity at any time. So my goal is to find v of just some time t. So in both cases, I'm going to integrate because I know velocity is the integration of a dt. So the first thing I'm going to do on this side is I'm going to just integrate the acceleration term. Excuse me. I'm going to do the same thing here, but I'm going to put bounds in. 0 to little t, because I'm not trying to find the maximum. If I was trying to find the expression for the max velocity, I would put capital T in here.
Right.
But that's not the case. I'm just putting little t in here.
So we're doing little t to find the expression, not the
Exactly.
total value.
We're trying to find the expression of velocity at some time,
Right.
not at the end time.
Right.
No bounds here, here. Because there's no bounds, that means when I integrate, I gotta have a plus C term. Oh, you know, and I'm such an idiot because, god damn, I'm an idiot.
Oh, it's sine.
It's sine. There's no trick.
It'd just be
really easy. Okay, so now I'm going to integrate this. I'm going to get this becomes that's right. Okay, it becomes this flipped t over pi.
right.
A max cosine pi t over t, and is it times -1? Yes. And I knew that because the integral of sine a to the t is -1 over a cosine a to the t.
That's the chain rule.
That is some kind of rule. Over here, I'm going to do the same thing. Oh, plus c.
Right.
That's the whole point. Here, if I do bounds, I can do the exact same thing. Negative t over pi a max cosine pi t over t, evaluated from 0 to t. Now this is technically an incorrect expression. We've got to find what that c term is. So I know the velocity at time 0 is 0. So I'm going to put 0 in here. 0 equals... Wait, hold on. I feel like I'm skipping something right now. No, I'm not. But I gotta put 0 in for time, because at time equals 0, I put 0 in there.
Right.
So I'm gonna have 0 equals negative t over pi. Cosine of 0 is 1. This becomes a 1 term plus c. Obviously, solving for c, c is going to be the opposite of this. T to cancel 0. So z is going to be t over pi a max. So when I did this, I now have an expression. The velocity at any time is going to equal this original statement plus c, and the c term is that thing right here.
Wow.
I know.
That's amazing.
So if we put whatever time we have, we can put in here and solve for it. I should get the same thing over here. So what I'm going to do here is, now that I evaluated, I'm going to do it twice. I'm going to do the top bound minus the lower bound. So the top bound, even Mr. Kirschenbaum, it feels kind of hard with the math. I agree. I'm going to put little t in there so nothing really changes.
Mm-hmm.
Now I'm subtracting the lower bound. So now I'm going to subtract the.
Ah.
Put 0 in there, this becomes 1. So now I'm left with negative t over pi a max cosine pi t over t plus t over pi a max. These two things are now the same.
Wow. That's
So
amazing.
in summary, you can do it this way where you don't actually put stuff in here, but you have to solve for c, and that's what the beginning term is. Here you can put in the bounds, but again, the beginning term is we're going from 0 to t, ends up being the same thing. So this is our velocity function. We're about to now use it to find work. Pause.
Yep.
All right, now we got to find the work done. And to find the work done by the net force, well, work and velocity relate. The work is the change in kinetic energy, which is positive. And kinetic energy is 1/2 mv squared. So we're going to find the change in kinetic energy. That's 1/2 mv, say, final squared, minus 1/2 m v initial squared. Here's my velocity function. I'm going to put a 1/2 m. I'm going to say that the work done is 1/2 m, the final minus the initial.
Mm-hmm.
Now, at this point, let's solve for what the final velocity is. This is my entire velocity function. At final velocity, little t is big T. In other words, you saw from your original conditions that the acceleration max is when little t equals big T.
Right.
So we're going to put in big T in here. So I'm going to get negative t over pi, a max, cosine, and that becomes big T over big T, which cancels out that cosine pi,
Right.
plus t over pi a max. Cosine of pi, that's negative 1. So this becomes negative 1. That negative comes out here, becomes positive.
Whoa.
T over pi a max plus t over pi a max. So my initial velocity is 2t over pi a max quantity squared. I'm not going to do it again, but this time I'm going to put in time is 0, which is going to get this term, is that right?
Cosine of 0 is 1.
Cosine of 0 is 1. Okay, yeah, when you put, okay, good, thank you. When you put cosine of 0 in here, this just becomes these two things, so it becomes negative t over pi a max times 1 plus t over pi a max. That becomes 0, I believe, right?
I think so.
I believe so.
It also says it starts from rest, right?
God damn it.
That was our C term.
Yeah, that's really smart. Thanks, Noah. I should have actually thought that way. Then do the math, and you get 2m capital T squared a max squared over pi squared, which is 100% definitely the right answer.
Wow.
So again, what we did is we put in, we did the kinetic energy change, figured out what the max velocity is. That's when we put in the capital T in there and solve for it. And for the third one, it says find the, here, keep going.
Keep going,
This is
yes.
the simplest thing ever.
Okay.
The third one says determine the force at terminal speed. Okay, terminal speed, the acceleration is 0. So you don't have to do all this other stuff because there's literally no acceleration. Therefore, our net force equation is just the force of the tension minus mg sine theta equals ma, and terminal velocity is 0. So the tension of the rope is just mg sine theta. And that's it. Please rewind and make sure it makes sense. Thank you so much, Noah Ziffin. Thank you.